Hello all, my name is Muhammad Omar Shakil Ahmed, and today I'm going to present my research, Semantic Risk Scoring of Aggregated Metrics, an AI-driven approach for healthcare data governance. I will first go over what we mean by semantic risk scoring of aggregated metrics and why it is important in today's data landscape. After that, I will provide a better understanding of how aggregated metric tables work under traditional versus the proposed AI framework. Then, I will talk about the AI framework, how it works, and go over a few sample queries and AI output. Finally, I will discuss limitations and future work. As you all know, data is the new currency. The healthcare industry is increasingly using data to make data-driven decisions. These large organizations have multiple BI teams that handle large amounts of data related to patient care, donations, research, and operations. Each team owns its own data, and sharing this data across teams raises privacy issues, especially due to HIPAA and other compliance regulations. So, a robust privacy-preserving architecture is required. A proposed solution in such an organization is aggregated metric tables. These metric tables only contain the final metric required for business decision-making. For example, instead of sharing all raw data related to patient donation, the metric average donation per patient type can be shared. Using this approach prevents the exposure of the underlying raw data. Another strength of this approach is that the metric logic is owned by the raw data team. This metric can be loaded into a metric table and be connected to various reports or BI tools. Any change in the string logic also flows through the metric table and ensures consistency. However, even aggregated metrics sometimes face the threat of re-identification. I have proposed an AI framework to score the SQL queries and flag risky metric definitions before execution. As you can see on the left is the traditional architecture, where raw data is directly exposed and consumed in BI tools to create metrics. This does not offer any privacy or governance structure. On the right is a more robust aggregated metric structure. Data is transformed by the metric owners and added to the aggregated metric tables. Anyone who needs access to these tables can be provided access, irrespective of their team, since it does not expose any sensitive data. These metrics can then be used across multiple reports and even different BI tools, as the table contains the final metric and the logic does not reside in any BI tool. Now, let's take a look at the proposed AI framework. The AI framework has 5 steps. It takes the SQL query as input, which is then passed through a SQL parser. So this SQL parser breaks the query into a structure called an abstract syntax tree or an AST. This tree helps the system build a roadmap of what the query is trying to do structurally. CodeBird embedding. CodeBird is a special AI model trained on programming languages and natural language. It converts the SQL query into a numeric fingerprint that captures the underlying logic and the purpose of the request. By leveraging the pre-trained transformer architecture, this model avoids the need for handcrafted semantic rules and instead relies on learned representations to distinguish queries that may pose privacy risks from those that do not. Syntactic feature extraction. So this system helps in pulling out risk signals, like how many columns the query groups data by, or how many tables it pulls data from, or whether it uses sensitive columns like gender, date of birth, zip code. which, if used incorrectly, can make individuals identifiable. So these features act like checkpoints that help the system understand the risk level of the query. XGBoost risk classification. So once the system has the semantic fingerprint and the hand-picked risk features, it combines them into a single profile of the query. This profile is then sent to the XGBoost, a highly accurate machine learning algorithm that acts like a fake judge. So, it has been trained on a large number of SQL examples labeled as safe or risky, so it knows how to spot dangerous patterns. The model outputs a risk probability score of 0 or 1, which reflects the likelihood that the query may violate privacy norms. I apply a configurable threshold, typically 0.85, above which the query is automatically flagged as blocked. This threshold can be tuned based on institutional policies, legal thresholds, or operational risk tolerance. And then we have the explanation engine. So blocking a query isn't helpful unless you explain why. So the final part of the system is the explanation engine. This module reads the structure of the query from the AST and uses predefined templates to generate a human-readable explanation. For instance, it might say, this query groups data by title and shift, which may reveal individual identities because the group sizes could be too small. To test the efficiency of my model, I tested it on a synthetic database that simulates hospital data. This data table had fields like gender, zip, diagnosis code, and wait time. This table shows the fields I have identified as sensitive. When I run the queries through the AI framework, I set a threshold of 0.85. This threshold can be increased or decreased based on the requirements. As you can see here, I have three queries as examples. The first query, it has a sensitive field, zip, so the query is blocked. The second query includes gender and medical code, so the risk score is higher than the first since it contains two highly sensitive fields. It is also blocked. The third query is approved as it does not pose a threat. Traditional rule-based approaches to query risk detection typically rely on static filters or hard-coded blacklist, such as banning combinations like zip and DOB within the same group by clause. While straightforward, these systems suffer from three key limitations. They lack context awareness. For example, grouping by gender alone may be perfectly acceptable in many cases, yet a rule engine might flag it indiscriminately. Second, they are rigid and struggle to adapt to novel data patterns or edge cases that emerge in evolving BI environments. Third, they offer no mechanism for prioritization or explanation, so producing binary outcomes without confidence scores or rationale, which hinders transparency and governance. In contrast, the proposed AI-powered system addresses these challenges through dynamic, data-informed evaluation. Sensitive field detection depends on keyword matching. Currently, the system only takes into consideration hard-coded sensitive fields. In the future, this can be adapted to be dynamic. For example, it only looks for fields labeled as zip or DOB and does not take into considerations the different variations of the same field, like date of birth. Another thing is no runtime context. Because the current framework performs only static query analysis, it cannot assess group sizes or distribution patterns. So the future versions would or could incorporate metadata-driven heuristics. It also has limited support for complex SQL patterns. While the current implementation successfully parses and evaluates standard SQL queries, it may exhibit degraded performance when encountering advanced constructs such as CTEs, window functions, and deeply nested queries. The training data and the labeling process used to build the classifier may carry institutional biases reflective of the source environment. So, broader calibration across multiple healthcare systems would improve fairness. This framework provides a technical solution that enables this balance. Instead of relying on runtime data access or manual reviews, the system analyzes SQL-based metric definitions before they're executed. By parsing the structure of each query and combining it with semantic embeddings and syntactic features, the model predicts a privacy risk score using a trained XGBoost classifier. Metrics flagged as high risk are blocked and accompanied by a clear explanation such as metric groups by job title and shift, which may reduce group sizes below FTC thresholds. This approach allows organizations to safely publish aggregate metrics like readmission rates or department level wait times without exposing raw patient records. It also ensures that BI teams outside the data owning department, like fundraising or operations, can access needed insights. It supports pre execution validation, meaning risks are caught before any query runs against the protected data. The result is a governance tool that's not only compliant with HIPAA, IRB, and Zero Trust principles, but also practical for real world BI workflows. Overall, this system lays the groundwork for ethical AI in metric generation and collaborative data infrastructure. Thank you.